Uh, so welcome everyone to today's seminar. So we'll have Hulya Arguz from the University of Georgia. So please take us away, unless the hurricane stops us.
Thank you very much. Very nice to see you all and be here for this nice seminar. So I will tell you about KSBA moduli spaces today. And this is essentially about something we have been doing since the last couple of years, which was trying to understand mirror symmetry for non-compact Calabi-Yau treefolds. And a couple of months ago, related to this work, we put a preprint in February with Valery Alexeev and Bousseau, which is an algebraic geometry explaining how to understand the geometry of moduli spaces of KSB of low Calabi-Yau surfaces using this going via mirror symmetry. And in 1 or 2 weeks, there will be a related paper on the physics side, giving a physics explanation of the story about the construction of 5-dimensional superconformal field theories, which is more related to M theory. But I will today talk about this part, and I heard that the M seminar is not necessarily about M theory, so I'm happy that I will tell you about the algebra geometric side of the story. So the plan of my talk is as follows. I want to tell you about KSBA moduli spaces of toric surfaces and how mirror symmetry for Calabi-Yau treefolds in the toric setup can be helpful to understand these moduli spaces. I will tell you how these are defined. And afterwards, I will look at the non-toric setup and tell you how to understand KSBA moduli spaces of log Calabi-Yau surfaces using mirror symmetry for Calabi-Yau treefolds in the non-toric setup. And the main result I want to communicate today is that the KSBA moduli space of these, even if you're looking at non-toric low Calabi-Yau surfaces, the whole moduli space is still a toric variety up to a finite cover. So I will start telling what are these moduli spaces. They're straightforward generalizations of the moduli space of stable curves of Deligne-Mumford. So if you look at the moduli space of stable curves, known as the Deligne-Mumford moduli space, every point of it corresponds to a curve C, which is a reduced curve of arithmetic genus G, which has adverse nodal singularities, and together with a tuple of points P1 to Pn, which are distinct points on the smooth locus of C. And in addition, there is a stability condition requiring that the automorphism group of such a curve with these points should be finite, which is equivalent to saying that if you look at the divisor given by the sum of the canonical divisor with this union of points, this should be ample. Okay, so it is known that this Deligne-Mumford moduli space is a proper Deligne-Mumford stack of, and you can calculate its dimension. And a straightforward generalization which satisfies analogous nice properties is defined by Kollár Shepherd-Barron and Alexeev, known as the KSBA moduli space or the moduli space of stable pairs. In this situation, it's consisting of pairs YB. The points of this moduli space are given by such pairs where Y is not necessarily a curve, but a projective variety, and B is a divisor in Y. And the analogous condition of such pairs, like in the curve case, we want to have adverse nodal singularities. The higher dimensional analog of a nodal singularity is known as a SLC singularity or semi-log canonical singularity. And I will not tell too much about this, but you can visualize it just in one-dimensional situation. It reduces to being nodal. And the stability condition is, again, analogous, saying that the divisor given by the sum of the canonical divisor with this divisor B you have on Y should be ample. And one difference, unlike in the previous case, is that it's not true anymore that each connected component is irreducible, though they're still properly Mumford stacks. And general goal in the setup is of people who work on KSBA moduli spaces is to describe the geometry of irreducible components of the space. And this was done around 20 years ago in the toric setup by Alexeev. And I will review what was done there first before telling what we did in the non-toric setup. So just to recall some facts about toric varieties. Toric varieties are pretty combinatorial. They can be understood out of polytopes in Rn. If you have a lattice polytope P in Rn, from this you can understand the data of a polarized projective toric variety, which I will denote by YDL, where Y is the proj of the monoid algebra, where you look at the monoids of integral points inside the cone over P. So when you have a polytope by CP, I denote the cone over P, and I consider the monoid of integral points inside this cone. And D is the toric boundary divisor, which is given by the union of torus fixed divisors, which is an anticanonical divisor in Y. And L is an ample line bundle. And when you do toric geometry, when you draw your polytopes, it is known that this ample line bundle that corresponds to this data has sections which are having a monomial basis that are in correspondence with whose elements are indexed by integral points in your lattice polytope. So for instance, for the canonical bundle O3, you have this polytope and you have sections that are indexed by the integral points. And here, if you just consider this toric variety corresponding to this diamond-shaped pink thing that I draw here, you can obtain this by chopping off 5 triangles of normalized area 1. And this will give you the blob of P2 at 5 points, though they are not going to be generic points. You will obtain a singular that puts a surface out of this shape, again with the anticanonical polarization. So generally, only if you have a single interior integral point, this means that the polarization determined by this polytope in toric geometry is going to be the anticanonical polarization. I wanted to draw this singular Del-Pezzo surface because I will use it as a running example. So if you look at the KSBA moduli space, which I denote by MYDL, it's defined as the closure of all stable pairs Y, and as a divisor, I'm taking D plus epsilon C, where D is the toric divisor, toric boundary divisor, epsilon is a very small number, close to 0, positive number, and C is any curve in the linear system of L. And one can show that if you take epsilon small enough, this modular space will be independent of the choice of epsilon, and it will consist of only torically transverse curves in Y. So this modular space will be like, if you look at the toric variety whose polytope is this, the singular Del-Pezzo, will be the modular space of all curves C, which do not intersect the zero-dimensional strata of the toric boundary divisor. So such curves are typically called torically transverse. And in the toric setup, this is what we're looking for as the KSBA moduli space. And in this situation, Valery Alexeev showed that the normalization of this moduli space is going to be a toric variety, and the associated fun to this toric variety is the secondary fun for the momentum polytope of YDL. So whenever you have a polytope of a toric variety, There's the dual fan, but there's another fan you can associate to a polytope. It's called the secondary fan. You can see it's also called sometimes the GKZ fan because it's defined by Gelfand, Caprano, and Zelewinsky in this book. And roughly, it's a fan whose maximal cones are in correspondence with regular triangulations of your polytope. So whenever you have a polytope, you can look at all possible regular triangulations. So in our diamond-shaped polytope, you have these possible triangulations. And you can draw a fan, like in the blue picture, I drew the brace of the fan of P2 in blue. And the maximal cones of this fan will be in correspondence with regular triangulations of this diamond-shaped polygon. Okay, so in particular, from this picture, one can deduce that if you look at the KSBA moduli space of the singular del Pizzo surface, it's going to be the toric variety P2. That's what Valerie's result says. And just to give an intuition on why this space is a toric variety, so if you consider all the divisors given by sums of given by equations APZ to P equals 0 indexed by integral points, where ZP denotes a monomial basis. So if you consider all divisors in the linear system of your ample line bundle, and you impose the condition that your coefficients should be in C star, then it will automatically be true that such a divisor, or if you're in dimension 2, such a curve like here, is going to be torically transverse. And the space of all such divisors form a torus C star to the number of coefficients, and up to reparametrizations, you will get a torus of dimension, the number of integral points in Z minus the dimension of your variety minus 1. And what is shown in this result of Valerie is that if you look at the secondary fan, this determines the toric variety which compactifies this torus C star to this dimension, because each triangulation actually determines the data of a toric degeneration of your variety. And all torically transverse curves, like here, if you have this triangulation, it will determine the data of a degeneration of your toric variety corresponding to the singular del Pizzo into two toric varieties whose polytopes will be these, each will be these triangles. And what is shown in that paper is that each torically transverse curve under such a degeneration will degenerate into a torically transverse curve. So these will tell you the boundary strata on how to compactify this torus. And eventually the KSBA moduli space is going to be the toric variety determined by the secondary fan. So I want to give an alternative, I want to describe an alternative interpretation of, what is the KSBA moduli space using mirror symmetry. And the reason for doing that is, well, if you do toric geometry, you have these polytopes, you can look at the secondary fan. In the non-toric setup, we do not have this notion of secondary fans or secondary polytopes. So I want to tell you an alternative way on how we can visualize the KSBA moduli space, which goes via mirror symmetry. So if you look at the threefold, Calabi-Yau threefold, given by the equation uv equals f of xy, where f of xy is a Laurent polynomial. So if you're given a polytope P such that the Newton polytope of F corresponds to P, then you can consider this equation uv equals f of xy. This will determine your Calabi-Yau threefold. If y is a toric variety, outside away from the toric boundary, it will be a non-compact Calabi-Yau threefold, which arises as an affine conic bundle over y minus d, which in the toric setup is going to be C star square if you look at the toric surface. So away from a curve defined by the equation f of xy equals 0, you will just have a copy of C star on the fiber, and over the curve, you will just have the singular thing which you can obtain by shrinking this to a point, shrinking the circle to a point. And one can show that the KSBA moduli space MYDL is the moduli space of complex structures, or the complex moduli space of the Calabi-Yau threefold. Because in our previous discussion, we said that the KSBA moduli space is just the moduli space of all such torically transverse curves. So if you look at the complement of the toric boundary, each such curve will correspond to a torically transverse curve. And furthermore, one can show that if you just change the equations of f, which amounts to changing such curves, then what you're doing is changing the complex structure of this threefold. So one way to interpret the KSBA moduli space is as the complex moduli space of such a threefold, and mirror symmetry suggests that it should be the same thing as the Kähler moduli space of the so-called mirror to Z. And in toric geometry, if you start with a toric variety like Y and construct this threefold, then you can understand this mirror of this threefold purely combinatorially. So the mirror Calabi-Yau threefold, which I denote by x bar, the mirror to Z, which by abuse of notation often we call the mirror family to YDL, following like mirror symmetry for surfaces. And because you can totally understand this threefold C out of the data of YDL, the mirror can analogously be understood just out of the data from YDL. It's going to be a singular toric variety, which has a map to A1, and you obtain the singular toric variety by looking at the momentum polytope for Y and taking the cone over it, and weave the cone over P, and weaving it as the momentum polytope image for this x bar. So toric mirror symmetry is essentially changing. So you view this as the fan image, toric fan for x bar. So toric mirror symmetry is essentially exchanging the cone and fan pictures. So if you have the momentum polytope of P, you want to understand the mirror, you want to weave it as a sort of a fan. So you take the cone of it and weave it as the fan of the mirror. And mirror symmetry generally do not want to work with single varieties. We want to work with families. So we will talk about the mirror to a maximal degeneration of YDL. So, like mentioned, the data of subdividing the momentum polytope of Y determines the degeneration of it. And if you want to describe the mirror of such a degeneration, then you're taking the cone over all such, the cone over the subdivided thing, and this will determine a Crepont resolution, which we call the mirror of this associated maximal degeneration of YDL. So this is toric mirror symmetry, and the expectation of mirror symmetry says that this moduli space, the Kähler moduli space MYDL, should be a toric variety, and the cones and the associated fan should be Kähler cones, whose analogs in the algebra geometric language are Neff cones. It's shown in earlier work of Hacking Keel in the situation if you know that if you have a nice algebraic space, if it's a Mori dream space, then you can talk about the Mori fan, which is a fan whose each of its cones corresponds to Neff cones of all possible Crepont resolution of your variety. And if you have a Mori dream space, it's known that these glue together if you add some additional Bogus cones, which are totally determined from these nav cones, all these glue together to form a toric fan. So if you have a Mori dream space X bar, you can look at all possible Crepont resolutions, look at their nav cones, and they will give you what is called a Mori fan. So the Mori fan is expected to describe the KSBA moduli space. In this situation of this diamond-shaped del pizzo singular del pizzo of degree 4, one can show that the Mori fan is indeed P2. And it is shown that it is shown in the work of minimal model people, Birka, Koshini, Haken, McKernan, show that if you have a Crepont resolution of a canonical singularity, this is always going to be a Mori dream space. And if you have a toric variety, it follows from the definition of the Mori fan that the Mori fan is always going to be equal the same fan as the secondary fan for your associated polytope. So now in the non-toric setup, we do not have the data of a polytope nor a secondary fan, but our goal is to describe the Mori fan and to show that this will give a toric variety, which will be the KSBA moduli space. So in the non-toric setup, the definition of the KSBA moduli space goes as follows. We fix a polarized Calabi-Yau surface YDL, Y is a projective surface, and D is a reduced anticanonical divisor, and L is an ample line bundle. And such a surface is typically obtained by doing non-toric blowups on a toric variety. Or alternatively, the second way to obtain such a surface is to destroy the toric boundary. Like if you're a P2 and 3 lines in P2, this is a toric variety with toric boundary. But you can smooth out the intersection of one of these intersecting lines. You would get a line into conic, which will give you a non-toric boundary, and it will correspond to a local Calabi-Yau surface. And Hacking Keel show that every local Calabi-Yau surface is related to a toric model and can be obtained from a toric momentum polytope by applying some operations on it. And such polytopes are studied extensively when you do these kind of operations by Symington. They're called Symington polytopes. So the moduli space for local Calabi-Yau surfaces, analogously in the toric setup, is defined as the locus of stable pairs, which are deformation equivalent to YD plus epsilon C as before. And in our work with Valery Alexeev and Kollár Shepherd-Barron, we show that this moduli space up to a finite Kaba is still a toric variety. And this proves a conjecture of Hacking Keel Yu in dimension which was conjectured for any dimension, and so far known cases were for toric varieties by Alexeev and for del pizzo surfaces of degree n, where n is between 1 and 6, and we prove this for all possible local Calabi-Yau surfaces. So the proof goes via doing mirror symmetry. What we first do is, given a maximal degeneration of a local Calabi-Yau surface, we explain how to construct a mirror called a semi-stable mirror to such a surface. And then we show that we can obtain a semi-stable mirror or construction as the Crepont resolution of an affine threefold singularity. Hence, the semi-stable mirror, we show it follows by results of minimal model program that such a mirror is a Mori dream space, so we can talk about the Mori fan of such a mirror. And then we show that this Mori fan is actually parametrizing the moduli space, the KSBA moduli space of all such pairs YDL. So to show that, we look at the double mirror. So using intrinsic mirror symmetry, the intrinsic mirror symmetry framework over the toric variety M sec, which is a toric variety, by which I denote the toric variety with Morifan X, whose Morifan is X, we show we can construct a family by DL. And furthermore, we show that this family has general fiber, which is deformation equivalent to the original YDL. And furthermore, that this family consists of KSBA stable pairs, namely it satisfies the stability condition. And hence, we conclude that this M-sec, this toric variety, whose fan is the Morifan of the mirror we construct, is indeed parametrizing the KSBA moduli space. So it's the toric variety we were looking for, which is up to a finite cover, the KSBA moduli space. So I'm not sure how much I would like to dwell into the proof. Maybe the proof is maybe due to uncertain weather conditions. Maybe I might skip the proof, and while I still have some power and electricity, maybe I can answer your questions if there are any at this point. Am I still there?
Yeah. I think you can go into the proofs.
Okay, shall I go into the proof? Okay.
So.
Okay, so the proof goes as follows. So the first step is to construct a mirror to a maximal degeneration of IDL. And the reason we needed to develop a mirror construction is because the so far available mirror construction in the literature do not cover such maximal degenerations of low Calabi-Yau surfaces. So in mirror symmetry, in the framework of mirror symmetry of low Calabi-Yau surfaces, there's a work of Hacking Keel, which constructs mirrors to only single YDL. So it wouldn't concern maximal degenerations, or it would concern only trivial degenerations. And in the more recent framework of mirror symmetry, intrinsic mirror symmetry of Grossi-Bab, they do construct mirrors to maximal degenerations of arbitrary Calabi-Yau or log Calabi-Yaus, however, with the technical assumption that such degenerations should be so-called log smooth, and these degenerations in the KSBA moduli space are typically not log smooth. So we needed to describe how can we construct or understand the mirrors of such maximal degenerations. To do that, we start with, this is an overview of the mirror construction. We start with the maximal degeneration of a low Calabi-Yau surface. So this is a degeneration where you degenerate as much as possible so that the central fiber will be eventually a union of P2s. And then there's an associated Symington polytope, like here I drew, to such a low Calabi-Yau surface. Just to illustrate, a maximal degeneration amounts to dividing everything as much as possible. And then you view this triangulation of the Symington polytope as this determines such a degeneration, and this will be the intersection complex of the central fiber of such a degeneration. And following ideas of intrinsic mirror symmetry due to Grossi-Bab, we want to view this intersection complex of our original degeneration as the dual intersection complex of the mirror we want to complete. So we want to view this as the dual intersection complex of a surface, of a normal crossing surface, X0, and then we will describe the mirror as smoothing of this normal crossing surface. So by the previous results of Engel and Friedman, any low Calabi-Yau surface has a Symington polytope, and you can obtain the Symington polytope so that it looks nice in the sense that there's a central point inside it, and you can join the central point to the vertices of your polygon. So this will give you a triangulation of your toric polygon. And they explain how to obtain a Symington polytope for any low Calabi-Yau surface by chopping off triangles on the boundary, which fully lie inside these triangles you obtain by joining to the central point. So we use this model, starting with social triangulation. We first show that you can subdivide always such a Engel-Friedman type polytope. You can always get a so-called coherent triangulation. So this is a rather combinatorial result by applying some so-called pooling construction, which appears in the literature. You can always subdivide it. And out of this data, we explain how to construct a normal crossing surface whose dual intersection complex is this subdivided Engel-Friedman polytope. So the irreducible components of such a normal crossing surface will be in correspondence with toric varieties. If you have a point like here around which you see a toric fan, these will be like smooth toric surfaces. If such a point is on the boundary, you will get non-compact surfaces. But if such a point is at the tip of a singularity, affine singularity, where you chop off a triangle, then we need to do some deformation theory to say what will be the corresponding irreducible component of our normal crossing surface will look like. And we show it will be a smooth low Calabi-Yau surface, which we can obtain as by some deformation theory. And then afterwards, once we construct such a normal crossing surface, we show that we can smooth it. So once we describe all irreducible components of this normal crossing surface, we show that you can glue those irreducible components in a natural way, and then you will obtain the normal crossing surface x0, which you can smooth to a threefold x. And we furthermore show that the total space is smooth plus the x0, the central fab, is a reduced normal crossing divisor inside it, which means that we can visualize the total space as a semi-stable degeneration. That's the definition of semi-stable. And furthermore, it's quasi-projective with trivial canonical bundle. And furthermore, to be able to obtain Mori fan associated to it, we need to show that it's a Mori dream space. And we prove that indeed you can find a contraction to some affine threefold with canonical singularities, such that you obtain a projective crepant resolution x to x bar, and furthermore, x is a Mori dream space. So now this is our semi-stable mirror x to a maximal degeneration of YDL, which is determined by subdividing the associated Symington polytope of YDL. So using this x, we look at the Mori cone of x. So first, to claim that the Mori fan of x will determine a toric variety which will parametrize the KSBA stable.
Can I ask a question?
Sure.
Yeah, so why do you say this construction is the mirror, right? And kind of making maybe a kind of philosophical point, right? So is this kind of in analogy to what happened to the toric case? And you
Right. So there are several different viewpoints on how you view mirror symmetry depending on your interests. So just as a philosophical question, as a philosophical remark, there is like categorical mirror symmetry as well as mirror symmetry, and each have different proposals on what should be mirror and which properties should mirror satisfy, and relating each of them is a subtle point. But here in the Gross-Seibert framework of mirror symmetry, which is more compatible with SYZ, so when you construct mirrors, they're expected to satisfy like dual torus vibrations. They will arise as dual torus vibrations, one can show, and it's compatible with the toric. Like it's a natural expectation that the non-toric mirror should be a deformation of the toric mirror. But furthermore, what we do is, like, if you believe that Gros-Seibert calls something mirror, they didn't have a way to talk about the double mirror. So what we do is construct the inverse of Gros-Seibert mirror, and we come back to where we are. So Gros-Seibert has a mirror construction, but like the recent mirror construction, like 20 years ago, they had a mirror construction for toric degenerations, and they could talk about double mirrors. Like, you take the mirror of something and then take the mirror of the mirror, you come back to itself. But in the recent mirror construction of Gros-Seibert, when you start with arbitrary Calabi-Yaus, which are like log smooth degenerations, you cannot go back because the mirror you construct is no more log smooth, is no more log smooth. So there was no way to come back. And what we do is we provide a construction, and we do show that if you do like our construction followed by Gros-Seibert, like if you start with YDL, apply our construction, and then we apply Gros-Seibert, you will get a family indeed, where you do see that we prove that in this double mirror family, you do see the general fiber. So it gives the right double mirror. It's the correct inverse Gros-Seibert mirror in some way. So what we do, our construction is essentially providing a way to talk about mirrors of degenerations which are not log smooth, and it's a good indication that when we run our mirror to such degenerations followed by the Gros-Seibert mirror, we obtain a family where the general fiber is diffeomorphic to what you start with.
Okay, thank you.
Sure.
Yeah, sorry, I also have a question about this picture. How good is MSEC? So it's a finite cover of the moduli space. Is it smooth? Like, is it irreducible? Do you know?
Right. It's not smooth. The KSBA moduli space is not smooth. We're talking as it's going to be irreducible because we're looking at a component of an irreducible component of the KSBA moduli space we're describing here. But it's a Deligne-Mumford stack. And during all of this talk, I'm always, whenever I talk about the KSBA moduli space, I mean the coarse moduli space, and I skip subtleties about
Sure.
stacky points and the stacky structure.
Sorry, I'm confused now. Are we talking about MSEC or MYDL? So MSEC is a toric variety, right?
Yeah, right. I'm claiming that, yeah, so the conjecture is MYDL is a toric variety. And I'm showing that MSEC is actually going to give you MYDL, and MSEC is a toric variety. So MSEC, I will construct a toric variety by going to the mirror and taking the Mori fan, and MSEC is the associated toric variety. And we are proving that this MSEC is exactly the KSBA moduli space. Up to sometimes you need to pass to a finite cover. Sometimes it's not exactly the KSBA moduli space, but it's a finite cover of the KSBA moduli space, which has to do with when you obtain log Calabi-Yau surfaces, you blow up a bunch of points, and there are choices of the ordering of the points. But if you blow up, for instance, only one point, it will be exactly the KSBA moduli space. So we construct MSEC, and the main thing is to prove that this MSEC is indeed the KSBA moduli space, MYDL, to relate it to the definition. And to do that, we show it parametrizes all stable pairs, which are deformation equivalent to YDL by the definition of the KSBA moduli space. So what we need to show that there is a total space over MSEC, which I denote by curly YDL, such that each fiber is a stable pair, and the general fiber is deformation equivalent to YDL.
Right, thank you.
Sure. Any other questions at this point? Okay, so we are constructing a semi-stable mirror, and because it's semi-stable now, it is all satisfying all nice properties where you can apply Gros-Seibert mirror symmetry and talk about the mirror family, and Gros-Seibert will show that you can obtain a family of low Calabi-Yau surfaces over this toric variety. And the subtlety in our proof is to show that when you obtain the stable mirror family, we need to show it's KSBA stable. It's a KSBA stable family, and showing something stable is technically a subtle point. I will mention about the proof soon. Okay, so once we construct this mirror, we prove it's a Mori dream space, so you can talk about the Mori fan and the associated toric variety M-sec. And then Grosebo tells you that there's a family of low Calabi-Yau surfaces parametrized by this M-sec. So generally, in the framework of Grosebo mirror symmetry, if whenever you have a semi-stable family of low Calabi-Yaus, like we construct, you can construct the intrinsic mirror as the proj of some algebra, which is called the algebra of theta functions, where coefficients will live in will come from the monoid ring NEX, where NEX here denotes the Mori cone, which is the cone of effective curve classes NX. So here I denote by NEX the monoid of integral points inside the cone of effective curve classes. And then there will be generators of this algebra in the Grosebo mirror construction, and each generator is similar to the toric setup. You can weave as indexed by some integral points and some combinatorial data, and this data will be the cone. These will be indexed by the integral points and the cone over the polytope. So this is what Grosebo says. If you have a semi-stable degeneration, you can construct a mirror. And the subtlety is this works only for semi-stable degenerations which are projective. In our mirror we construct, we want a projectivity, so we need to generalize this construction. And to generalize this, we show that you can we show that things converge. Essentially, there are some technical details to show this construction can be generalized to non-projective things. And then we furthermore show that while in the Grosebo construction you obtain the mirror as a formal family, only by some convergence results, you can extend this family over the affine toric variety. You can obtain a family over spec C and E, spec C of this monoid ring, which gives you a toric variety. And by convergence properties, I mean that in this mirror construction, there are structure constants which are obtained as counts of punctured log maps. We show that when you fix a curve class, you can obtain only finitely many such punctured log maps and things converge, so we can extend this. And then we show that we can also define, we don't only want to construct a mirror, but we want to define a divisor, because we want to talk about K-space stable pairs, which are pairs given by surfaces and divisors into them. And we want to obtain the total space also as a threefold with a divisor, so that when we restrict to a fiber, it will give a surface and a divisor inside it. So we describe a divisor by looking at all theta functions, these thetas which correspond to the interior of this cone over the Symington polytope. We show this defines the divisor, and furthermore, we also show you can consider the natural line bundle, and then you will obtain this pair YDL. And furthermore, we construct a mirror not only for a single Crepont resolution, but for every possible Crepont resolution of this threefold with canonical singularities. And then we prove that all these mirrors glue together to give you a family of stable pairs, stable surfaces over this toric variety. So to obtain this family, we need to use some gluing arguments of all possible mirrors of all possible Crepont resolutions, and this uses gluing formulas in punctured log Gromov-Witten theory. And then, we show that once we construct a stable mirror by this gluing, this family is K-space stable, and this K-space stability is a major technical chapter, and furthermore, we prove separately in another chapter that the general fiber is deformation equivalent to what we started with. Okay, so I will skip the proof of this. And finally, we prove that this MSEC, which parametrizes, as what we showed, K-space stable surfaces, we show that okay, once we know it parametrizes surfaces which are K-space stable, by the universal property of the K-space moduli space, we obtain a natural map from this MSEC to MYDL. And then we prove that this map is finite and surjective generally. Like in many cases, you don't need to worry about finiteness. Like if you blow up only one point to obtain YDL, it will be just equal to the K-space moduli space. But generally, we obtain a finite and surjective map. And this completes the proof that I mentioned here, that the moduli space MYDL of polarized Calabi-Yau surfaces up to a finite covers a toric variety. Okay, I think this is all I wanted to tell you about today. I'm happy to stay if you have questions, or if I can go through anything further.
Thank you. So in that example, right, that you had this non-toric P2, right? So this moduli space is P1, right? The KSBA, right? So is this in general compact? Or
yes, KSBA moduli spaces are always
moduli space that you get in the end. This
right, the moduli space at the end is always going to be a
always compact,
complete toric variety, right? In this example, as you said, we get P1. So to obtain a complete toric variety, so it's a pseudo point about the construction of the Murray fan. You need to sometimes complete by adding bogus counts. Like even in the toric situation, like here, when you just look at the KSBA moduli space of this diamond-shaped delpizzo of degree 4, then in this delpizzo of degree 4, let me come to this Murray fan picture. You have only one Crepont resolution of this. If you look at the mirror, which is like X bar is like the cone over the diamond-shaped thing. X is the projective Crepont resolution of X bar, which is obtained by weaving this as the fan. So this is the only smooth projective Crepont resolution of the mirror. This gives you a Neff cone, which is the cone of A1. And to complete it to compact toric variety to obtain P2, you need to have some with so-called bogus cones. And in the non-toric setup, we have analogs of such bogus cones, ensuring that we obtain compact complete toric varieties. So once you know all possible Crepont resolutions, you describe all their Neff cones, like the Neff cone to this thing, and you have these triangulations which give you other like partial Crepont resolutions. If you just take X prime and X prime prime, the toric varieties whose fans are the cones over these triangulations, then they will be related to this Crepont resolution in a way that you contract a copy of P1 times P1 to go to here. And the nefcones of these things are of lower dimensional. So to complete it to total fun, you need to remember what you contracted to go to here and add a ray generated by this what you contract. So if you remember all possible nefcones, and if you remember all possible divisorial contractions, there's a recipe to produce a complete fun. The Mori fun will give a complete fun, and it will correspond to a projective toric variety, which is compact. And this is the recipe provided by Keel. And in our non-toric setup, we also consider not only all possible nefcones of possible Crepont resolutions, but we sometimes add these Bocuse cones here. And furthermore, there's a technical detail that I skipped. If two cones differ by an M1 flop, we identify them to get our finiteness. But yes, at the end of the day, what we obtain is a compact projective toric variety.
Okay, thank you. So, any questions? Last chance before the hurricane arrives.
I just had a small question about torically transverse divisors. I think it was on slide 7. Those just avoid the fixed points.
Right, so here torically transverse divisors are just, if you're on a surface, they're just curves which do not intersect the zero-dimensional strata of your toric boundary. So they're here, they do not go to the corners. Like if you have 4 lines formed by your toric boundary, each intersecting at a point, you want C not to go through those points, singular points.
That made sense. And then on slide 9, so there was a way to write them down if we just have non-zero coefficients on the monomials over the lattice point.
Right. These will all give torically transverse divisors. So I'm taking the toric monomials here. So this is to ensure you get an element in the linear system of your ample line bundle L. And indeed, once you have non-zero coefficients here, you ensure that you're intersecting somewhere in the interior of the toric boundary. If you look at this equation and restrict to the toric boundary, so imagine this is a P1, it is a 0 and infinity, and everything in the interior is a C star orbit. So ensuring that coefficient is non-zero ensures you that you're landing somewhere in the interior of that C star and not going to the endpoints, which are either 0 or infinity.
I see. Then on slide 16, what we were just avoiding strata? Was it avoiding zero-dimensional strata or what?
Let me see, slide 16. I have this 14, 15, 16. Okay, I have this. Okay, in slide 16, sorry, say again here.
I thought this was a generalization of being torically transverse, but we weren't just avoiding the fixed points.
Absolutely. So in the situation, in the non-toric situation, you're looking at stable pairs YDL, which so you're looking at pairs Y with the divisor you take as D plus epsilon C. And there are 2 conditions you need to satisfy by the definition of KSBA moduli space. Such a pair is in the KSBA moduli space. First is about the singularity condition that needs to have SLC singularities. And this is about avoiding the strata. So you can ensure that such a pair will have it's about the SLC condition, it's about the pair. It will satisfy this having semi-log canonical singularity as long as your C is avoiding the zero-dimensional strata analogous as in the toric situation. And the second condition was the stability condition. You want to ensure that if you look at this divisor and sum up with the canonical divisor, then you need to get something ample. But this divisor, this toric boundary divisor is anti-canonical, so ky plus t will just cancel out. And as long as you take an ample C, this will automatically be ample. So the stability condition is always automatically satisfied when you look at such pairs. That's why we take a weird divisor looking like d plus epsilon c. The stability is nothing to worry about, but we need to worry about satisfying the SLC condition, and one can show that as long as you take C such that which won't go through the singular points of the boundary, you can satisfy the SLC condition. That's correct.
I see. Thank you very much.
Thank you. Very good questions.
Okay, any other questions? No? Okay, so I guess that's it for today's seminar. Thank you a lot.
Thank you very much for the very good questions. It was very nice meeting you all. So I'm sorry I was slightly bit nervous because electricity is going on and stuff. So if it's once a bit sloppy and if you want to discuss further, you can drop me an email. Hopefully after 2 days, we will be in better shape here. We will have continuous internet and so on, hopefully. Okay, thank you very much. It was very nice meeting you.